logic 1. So this is the excitation table for SR flip-flop. Now we'll see JK flip-flop. JK flip-flop is designed by some modification in SR flip-flop. If you have this SR flip-flop with S and R input, this is clock input. This SR flip-flop can be converted into JK flip-flop by just having this additional circuitry. This input is as J and this input as K. So this flip-flop will be converted into JK flip-flop. Now using NAND gate, we will design this JK flip-flop. This is SR flip-flop. And this SR flip-flop can be converted into JK flip-flop by taking just feedback combination, feedback connections. We know that we will have to add here one AND gate, and this AND gate will be here S and R input of this flip-flop. See one thing, if we have a 3-input NAND gate, if one input is A, other input is B, and the third input is C, then in this case the output will be A dot B dot C full bar. And if we have two inputs passed through AND gate, output will be A dot B. And if this output is passed through an NAND gate with another input C, in this case the output will be A dot B dot C full bar. So this combination is equivalent to a 3-input NAND gate. So instead of adding here one AND gate like this, we will directly take feedback to the input of this NAND gate. So we will use a 3-input NAND gate. So this is the circuit for JK flip-flop, and now these inputs S and R input will be called as J and K inputs. Now we will draw the truth table for this JK flip-flop. There are two inputs JK and one clock output Q and plus 1 will be noted Q and this is Q and bar. Now we'll see the first combination. The clock by default will be mid 1 because when clock is 0, always the previous state will be there. If clock is 1, there will be 4 combination for JK 0 0 0 1 1 0 1 1. Now if J and K are 0, clock is 1, For this NAND gate, one input is 0. We know that in a NAND gate, if any input is 0, output will surely be logic 1. So for these two NAND gates, output will be logic 1. And we know that for a NAND latch, this is again NAND latch. For a NAND latch, if both the inputs are at logic 1, output will be in previous state. So output will be again Qn. This will be in previous state. Now the next combination will be 0 1. For this combination 0 1, this NAND gate will give output 1, but we cannot define the output of this NAND gate until we know that the value of this third input. So for this input combination, we will assume that the previous output is 0 1. So assuming the previous output, we could get the output of the second NAND gate also. This one will go in feedback here. Earlier we have seen that one input is 0, output this time also be 1. But if this 0 comes here, 1 1 0, and one input is 0, output will be logic 1. And for the NAND gate, we already have seen that if both the inputs are at logic 1, output will repeat itself. So previous output was 0, next output was 1. So in this case, we can say that output is repeating itself, but we cannot say that every time we'll do this, because the second combination will have to be considered, that is 1 0. What if the previous output is 1 0? So for this, if output repeat for this combination also, then we can say that for this combination 0 1, always a JK flip-flop have previous state in its present output. Now the combination is 0 1. This one will be in feedback here. This 0 will be in feedback here. Now for this for this NAND gate, two inputs are 0. One input is necessary to make its output as logic 1. So its output will be logic 1. And for this NAND gate, all the three inputs are at logic 1. So output will be 0. And we know that for a NAND gate, NAND latch, if input is 1 0, output will be 0 1. So we have seen that earlier we assumed that the output is 0 1. It was in previous state. If we assume the previous output as 1 0, we have seen that the output was altered. So whatever may be the output in previous state, next output will be again always 0 1. So for this combination 0 1, output Qn will always be 0. In the previous case, we assumed 0 1 output, it was repeated, and if we assume 1 0, it was altered by this flip-flop. So whatever may be the previous output, the present output will be 0 1, means Q will be at 0. Now we'll see the next combination. Next combination 1 0. J is 1, K is 0. So for this next combination again, we will define this output as 0 1. We are assuming the previous output as 0 1. If this 0 1, this 0 will come here and this 1 will come here. All the three inputs are 0, logic 1, logic 0 will be output. If one input is 0, output will be logic 1. And we know that for a NAND latch, if input is 0 1, output will be 1 0. So it is altering the output. But we cannot say that Every time it will alter the output. Every time it will toggle the output. So we will have to consider the next output combination as 1 0. This 0 will go in feedback and this 1 will go here in feedback. One input is 0, output will be logic 1. One input is 0, output will be logic 1. So in this case, for this NAND latch, both the inputs are at logic 1, and we know that if a NAND latch has both the input at logic 1, output will repeat itself. So in both the assumptions, so we obtained the next output as 1 0. Sorry, this will be 0. So in this case, if we assumed output 0, 1, next output was 1, 0. If we assumed output 1, 0, next output was again 1, 0. So whatever may be the output in previous case, the next output will be 1, 0. So Qn will have value 1 for 1, 0 input. Now we'll see the next combination of input. If both J and K are at logic 1, again we will assume the previous output as 0 1. This 1 will go in feedback here, this 0 will go in feedback here. All the inputs are at logic 1, output will be logic 0. One input is at logic 0, output will be at logic 1. So for NAND latch, if input are at 0 1, output will be 1 0. Means it is altering the output. But we cannot say that it will alter the output every time. It will toggle the output every time. We will have to consider the next combination 1 0. If the previous output is 1 0, we will see the next output. This 0 will go here and this 1 will go here. And in this case, all the three inputs are logic 1, this will be logic 0. One input is at logic 0, output will be at logic 1. In this case, for this NAND latch, inputs are 1 0. If inputs are 1 0, it will have output as 0 1. So this time also it is altering the output, means it is changing the output. Whatever may be the value of Q1, if inputs are 1 1, JK are 1 1, the JK flip flop will change its output. If Q1 is 1 in the previous case, it will make it as 0. If it is 0 in the previous case, it will make it as 1. So every time when input is 1 1, output will be complement of the previous output, that is Q1, and this state is called toggle state. So a JK flip flop will toggle when both the inputs are at logic 1. Now we'll see the characteristics table. Again, the output will depend on J, K, Qn. Qn plus 1 depend on all these. 3 variables, 8 combinations. Qn plus 1. We know its truth table. JK 00011011. For this JK combination, Qn plus 1 was Qn, hence repeating itself 0, 1, and for 1 1 it was complement of the previous output. So when J and K are 0 0, the output was in previous state. So for this the output was 0, for this the output was 1. When 0 1 is JK, 0 1 is JK, output was 0. If input JK is 1 0, output will be 1, 1 0, output will be 1 according to this table. And when input jk equal to 1 1, output was complement of the input. Output was complement of the previous output. So when j and k is 1, output was complement of the previous output. If previous output is logic 0, next output is logic 1. If previous output is logic 1, next output will be logic 0. For this characteristics table, now we will solve for qn plus 1. Again, there will be three variables j, k, and qn 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. And qn plus these values will be plotted in this k map 0, 1, 0, 0, 1, 1, 1, 0. Now we will do pairing these two ones and these two ones will be paired in this k map. Now we'll write the equation for qn plus 1. For this pair, it will be so. First we'll write for this pair. For this pair, j equal to 1. That is j, and k is changing while qn is 0. So j qn bar plus. For this pair, j is changing but q is constant 0 k bar, and qn is constant 1. That is qn. So the characteristics equation for JK flip flop is this one. This is characteristics equation for this JK flip flop. Now we'll see excitation table. Earlier we have seen excitation table for SR flip flop. Similar will be the table for JK flip flop with some changes. So if previous output is 0, next output is 0, we will predict what was the value of J and K. 0, 0. And for this combination is this. J is 0, confirm. K is changing, so will be written as cross. Now the next, if previous output is 0, next output is 1. This one, this one. For this combination is this. For this combination is this. In both the cases, J is 1, but K is changing, will be written as cross. In the next case, previous output is 1, next output is 0. In this case, the combination of input is this. K is confirmed 1, but J is changing, will be written as cross. And in the last case, if previous output is logic 1, next output is also logic 1, this one, this one. For both the combination, the for both the output combinations, the JK values are like this. J is changing, will be written as cross. K is 0. So this is the excitation table for JK flip flop. The advantage uh, of this JK flip flop is that for 1-1 input combination, we are not getting invalid output. And one disadvantage we have for this JK flip flop is race around condition. Race around condition. This is the disadvantage of this JK flip flop. Now we'll see D flip flop. It is also called as delay flip flop. A D flip flop can be obtained from SR flip-flop or JK flip-flop. Suppose this is a flip-flop which is either SR or JK flip-flop. This input is S or J, this input is R or K, and this will be its output Q and Q bar. Now in D flip-flop, D flip-flop can be obtained. It is a single input flip-flop which goes directly to S and it is inverted and connected to K. Now this flip-flop K is called as delay flip-flop. In delay flip-flop, as it has only one input, that is D, the truth table will contain here D, Q, N plus 1, and now if clock is 0, then like SR flip-flop, JK flip-flop, output does not depend on D and it remains in previous state. If clock is made 1, then output depends on D and depending on D output will be generated. If D is 0, then this input will be 1. Consider this as SR flip-flop. For SR flip-flop, one input is 0, other input is 1. For 0 1 input, SR flip-flop generates 0 at the output. Now consider the next case. If D equal to 1, then this 1 will go directly here and its inverted form, that is logic 0, will go to R input. If S input is 1, R input is 0, then this flip-flop will generate logic 1 at the output. So this is the truth table for D flip-flop. As you can see that the output Qn plus 1 is similar to or same as the input D. So this flip-flop is nothing but a delay element between input and output. Output Qn plus 1 is similar to the input, whatever may be the input, 0 or 1, same will be the output. This flip-flop is acting as a delay element between input and output, hence called as delay flip-flop. Now we'll draw characteristics table for this delay flip-flop. Output depends on input and previous output, as earlier we have seen in SR flip-flop and JK flip-flop. There will be two parameters on which output depends, Qn plus 1. As there are two variables, there will be 4 combinations. Now we know that according to truth table, whatever is the D, same will be the output Qn plus 1. So Qn plus 1 will be equal to D 0 0 1 1. Now solving the K map for Qn plus 1, putting these values, two variable K map, it will be a 2 variable K map 0 0 1 1. One pair, and from this K map we can directly write as Qn plus 1 equal to D. So this is the characteristic equation for delay flip-flop. Now we'll draw excitation table for D flip-flop. We'll require this characteristics table. Now if output changes from 0 to 0, what should be the value of D? We have to find out. If output is changing from 0 to 0, D should be 0. Output is changing from 0 to 1, D should be equal to 1. Output changing from 1 to 0, D should be 0, and output changing from 1 to 1, D should be equal to 1. This is the excitation table for D flip-flop. Now the next flip-flop is toggle flip-flop, T flip-flop, also called as toggle flip-flop. A T flip-flop is obtained from a JK flip-flop. Remember, not SR flip-flop, only JK flip-flop can be used as a toggle flip-flop. If both the inputs are shorted and a common input is given, this flip-flop is called as toggle flip-flop. We know the characteristics or truth table of JK flip-flop. The truth table for T flip-flop can be obtained as: if clock is not applied, clock is 0. In this case, output does not depend on input T and it remains in output in previous state. Now, if clock is made 1, means clock is applied, now output depends on value of T. As T is single input, there may be a 2 combination. Now Qn plus 1 for T equal to 0. If T equal to 0, J will be 0, K will be 0. And we know that in JK flip-flop, if both the inputs are logic 0, output remains in previous state Qn. Now if T is made 1, both the inputs are logic 1. If both the inputs are logic 1, then JK flip-flop, we know that it toggles output changes from previous state every time. So output may be called as Q and bar, means with whatever may be the previous output, next output will be its complement. So this is the truth table for toggle flip-flop. Now we'll draw its characteristic table. Output Qn plus 1 depends on T and Qn. As there are two variables on which output depends, there will be 4 combination. We know that if T is 0, output Qn plus 1 is Qn. Qn is 0, so it will be repeated. We know that if T equal to 0, output is Qn, means previous output. Previous output is 1, it will be repeated. We know that if T is 1, output will be complemented. If T is 1, output will be complemented. Output will be complemented. So this will be the characteristics table for this toggle flip-flop. Now solving for Qn plus 1 will get its characteristic equation. Now Qn plus 1 will be plotted here. Now in this truth table, uh, there will be two singles, and equation can be directly written as Qn plus 1 is equal to T bar Qn plus T Qn bar, means output Qn plus 1 is T XOR Qn. T XOR Qn. This is the characteristics equation for toggle flip-flop. Now we'll draw its excitation table. Now if output changes from 0 to 0, means output is not changing. Output, previous output was 0, next output is also 0. Here t will be equal to 0. If previous output is 0, next output is 1, t will be 1. If previous output is 1, next output is 0, t will be equal to 1. Sorry, this will be 1 1. And if output, previous output is logic 1, next output is also logic 1, in this case the t input will be 0. So this is the